Okay, so we'll continue there. This is then sort of a bit at a higher level again from what we were just talking about. And so this is sort of these ideas of imperative versus declarative programming in terms of how you should think about the problems you're doing and how you should be writing code kind of from the very beginning if you have that freedom, which I guess many of you may not always have. So the idea of imperative programming is this is where you're sort of directly coordinating tasks on the computer. And so the example I sort of gave earlier was with this sort of micromanaging boss. And so when your boss comes over to you and tells you, I think you should read this part of this paper, and then I think you should bring this sample to the beamline, and then I think you should measure it at this energy, and then I think you should do this and this and this, and then I think you should export the results and then copy it to a hard drive, that it's incredibly detailed. You have very little freedom to think about what you're actually supposed to do, and you just end up sort of executing exactly what your boss says in exactly the order you're supposed to do it. And so this is sort of exact orders. You have a time ordering because everything needs to happen in order. Data management is manually controlled. Job and task scheduling is manual. And you have the potential to tweak and optimize performance. And so in some cases, this makes a lot of sense. You know, when you look at like the Formula One, when they go to replace a tire, when the car comes in, it's not, let's think about who should do what task, who has the drill. Like, it's very clear they do exactly these things in exactly this order that they've practiced this many times because this is the most efficient way to get it done. And so when you're trying to get really the top performance, having this sort of micromanaged imperative approach can be very, very advantageous. But it requires that you really practice and think and optimize your task a lot. And so for the Formula One case, it certainly makes sense to take this approach. But for many other cases, it may not. And when you look at sort of how much time you have to develop these processes and how much they're going to be used and how good you are at actually optimizing them, there's a trade-off that kind of needs to be made. And so when we look at sort of the making of the soup, we have a very simple example here where it's sort of buy vegetables at a market, then buy meat at a butcher, then chop carrots, then chop potatoes, then heat water, then boil, then wait, whatever those steps might be for making a very simple soup. And that the imperative is sort of the way it's shown here, where if you gave this to a robot and told them to do it, they would execute it, but there wouldn't really be any thinking that they could do. You know, if you wanted this to be done faster, you could maybe send 5 robots to do the same task and you'd get 5 soups instead of just 1. But to make it go quicker, there wouldn't really be too much you could do. Maybe here you could say chop potatoes, you could have 2 robots chopping. But in the way you've sort of given these instructions, there's no way for the robot to know that you don't have to buy the vegetables before you buy the meat, because you just gave it a list in this way, and it doesn't know that those things aren't dependent on each other. It just sees buy, then. And that's how you type code in MATLAB or C++ or Python or most of these languages, where it just ends up being a list of instructions that have to be executed in that order. And sort of the alternative approach to this is declarative. And so declarative is much more, has anyone heard of SQL before? SQL? Heard about it. And I guess Erlang, Haskell, Scala, no one's heard of, probably. Python and R can be declarative, but most of the time they're not. But basically, these languages focus much more on describing a task and much less on describing how it actually gets done. And so they're focused a lot more on goals instead of specific details. And so when we have the sort of boss example from before, rather than saying, bring the sample, measure it for this long, use this exposure time, ... your boss would say, I want you to get good images of the bone, go. And then you have to go and figure out exactly what the details are, and so you can solve that task. And so what happens with this is that from the computer perspective, data is automatically managed and copied. And so you don't explicitly say where which machine processes which bit of data, and it's handled for you. And scheduling is automatic. So it also figures out which processors or which machines should do which task at what time. But it's not always efficient. And so it's, unlike the F1 example, you sort of have a bunch of tasks that need to take place, and they may not always happen in the right order, but you don't have to worry about saying which one happens in which machine. And so when we look at sort of making a soup, what the difference in the instructions are is rather than having all of these thens, what we have is we have a bunch of independent sort of statements. And so there's no then, there's also no ordering here. And so what we say is, buy vegetables at market goes into shop veggies. Buy meat at butcher goes into shop meat. And then we have this task, wait for shop veggies, then chop carrots into pieces and put that into chop carrots. And so the idea here is that you have all of these tasks that you can execute in whatever order you want. But if you execute this one first, it won't be able to do anything until this one's finished. And so you've kind of created a dependency list or a hierarchy of the tasks in this description. Yeah?
Is there a problem with this code? Because it doesn't say you should wait for chopped meat before you turn the water and start adding water, adding meat.
Do we?
Wait for boiling water, chop carrots, chop potatoes, but not wait for chopped meat.
That's true. So we can fix that.
Not sure it's occurred to me.
Yeah. So I think we can. I think I wanted to keep it a little less detailed, but obviously having it wrong isn't good. Boiling water.
Sorry.
No, it's fine. Having wrong text there makes it probably harder to understand. Oop. Chopped carrots, chopped potatoes. And I guess, did I chop meat or something? No, I guess you just put meat in as it is. Oh, maybe you add meat here. Soup. Oh, I don't know what this would be. What is that? Broth?
Is it going to get updated right away on our laptop?
It won't get updated right away, unfortunately.
Oh, okay.
It's not all synced or anything like that yet, no. Broth. But if you go to the link later, it will have the correct version of this. So then wait for broth. We just call it broth. It's easier. Anyways. Okay, does that look right now or right-ish? I mean, this isn't computer code anyways. This is much more just to sort of show what are the dependencies, and that basically when you can break up your task into groups like this, you can make it a lot more, you give the person doing it a lot more freedom to do it however they want to get it done, and to scale the task out or down to whatever people want to do it. And so, yeah. And so when we look sort of what's the difference, and the difference really would here be if you want to get it to be done more quickly. That with the imperative soup, you have sort of these instructions here. The declarative soup, and this is the out-of-date declarative soup, but I'll update that later. That if you want to get this done quicker, the imperative soup, all you can do is you can say, okay, I'll make 5 soups at the same time, or I'll have these individual tasks done quicker because those aren't micromanaged for me. And with the declarative soup, you can basically give everyone a different task, and some of them will just sit there idly doing nothing because they're waiting for the veggies to be bought, or they're waiting for the water to be heated, or any number of other tasks. But fundamentally, you can divide this up into a number of different tasks and keep a lot of things busy. And if you look at the way normal computers work, even though this laptop only has I think, 4 cores in it. If you go to the task manager, there are, I think, thousands of processes running. And most of them are just waiting for other things to get done. Because in fact, this is a much more efficient design to just create all these separate things so that you can execute them all and run them in sort of as they're finished or as they're able to be run, and have the rest of the time them just be sleeping or waiting. And so this is sort of the mindset you want to have a little bit when thinking about these problems, is how can you create it in sort of as declarative of a way as possible. And as soon as you're manually managing data or manually scheduling the order of tasks, you've lost a lot of this declarative ability. And so when you kind of look for what the results for this are, for the imperative approach, you can optimize specific tasks, you can do many soups at the same time. You know, MATLAB, for the specific optimization of tasks, if you run a fast Fourier transform on a large array, it will automatically run this on different cores because it has fast Fourier transform as an operator that it can parallelize easily. But if you do a for loop, it doesn't know that it can run this on different cores, and you end up with a lot of problems trying to parallelize this. And declarative approach, you can basically run everything at once. Each core or computer takes a task and run it. And the execution order doesn't matter because each task sort of implicitly says what it's depending on and what it's waiting for. And so lazy evaluation is kind of a secondary benefit of this. And what this is that you don't really run any code at all. And so what you do is you build up sort of, this is how you make a soup. And if someone wants to make a soup, this is the instructions that need to be sort of followed. But you only execute what needs to be executed when someone needs to have it. And so when this comes in very handy, which we'll have examples of later, is if you're thinking about, you know, a terabyte-sized image that you're trying to process and you want to make sure your reconstruction looks correct, that you just want to look at 1 or 2 slices in the whole image. And so you don't need to process every single slice of the data set to get that output for 1 or 2 slices. And so if you have lazy evaluation, you can only execute the code and read and run the analysis that needs to be run for the exact output you're looking for. And so you don't end up doing all of these analyses before, even though you don't need them at all, because it's only executing what you need to execute to get the results you have. And so for the soup example, of course, that's, you know, if you never use tomatoes in your final result, then you never buy tomatoes. But if you follow the imperative approach, then it buys tomatoes because that was on the list of things it had to do, and that forces it to kind of execute. And then kind of the last point for this is that sort of one of the major challenges of these sort of experiments is keeping track of all the results in a clean, efficient manner and sort of doing all of these things well. And so when you have lots of different files to organize and data sets and parameters, it becomes sort of complicated. And particularly if you're using a lot of different tools like MATLAB, Excel, and R, it means a lot of rewriting code to get things to work together. And so that's sort of in addition to the differences between imperative and declarative, a reason for focusing on more declarative approaches, because you can keep yourself separate from all the data management for a longer period of time. So the things we'll quickly mention here is the idea of queue computing. So I don't know what systems you have at your home institutes, but if you're at Paul Scherrer Institute, you use something called Oracle Grid Engine. At ETH, you use a very similar variant to that. At some departments, you have something called Condor, which lets you use all of the computer lab computers in the background while they're not busy as a cluster. But basically, all of these systems offer what's called queue computing. And so where you have sort of resources, jobs, and users that you're trying to manage well, and that's what these systems do. And so resources are really, what is your cluster made of? And so this can be a collection of processors, of CPUs and GPUs. It can be memory or local storage. And so for some tasks that you're doing, you'll want to have 128 gigabytes of memory. And so that's a resource that you would have in your cluster that you could book. Access to bandwidth. So at some universities, you only have a few very quick accesses to the external internet. And so if you're downloading a bunch of data from Amazon, you want to have access to high bandwidth. There's also a number of institutes that have one 3D printer. And so if you want to print something out in 3D, then you want to sort of manage that resource so that it's shared between a number of users fairly. And then the last part is that sort of for a given period of time. And so all of these resources have sort of time that can be associated to them, like a meeting room, and you want to be able to schedule that well. So jobs are then a specific task that you're trying to run. So this is like an analysis that you're trying to do. And then the necessary minimal and maximal resources to run with. And so this often includes execution time. And so if you're doing a reconstruction, you'll say this should take less than 24 hours, or this should take less than 20 minutes. And if it takes more than 20 minutes, kill it. And then the last part is sort of the users, so account submitting jobs. And so this allows you to sort of share the resources between users fairly. Because as you'll see, many institutes, there's certain groups that have paid a lot more for the cluster than other groups. And there's some people that just submit jobs constantly. If you have a lot of data sets to analyze, it doesn't mean you should be able to use more of the cluster than someone else. And so you have these systems in place to sort of manage those resources, jobs, and users efficiently. And so whenever you work with these kinds of systems, those are the sort of things you have to think about. That what task am I trying to run? What resources does it need? And how can I be sure that sort of it finishes in a reasonable amount of time? And then the next part of this is really once you've come up with this task, how do you actually go about running it? And so here you have this idea of a master or name node. And this is the node that everything communicates with. The main address, the point of contact for everything that you're doing. You have the worker nodes where all the computation's actually done. And so these are all the nodes with the large amount of processing power or memory or hard disk space. And then you have the scheduler. And so this is the task that actually runs normally on the main node that takes into account all of the tasks and all of the users and the resources and tries to decide which user or which job runs at which time. It's also the task that goes about killing your job if you've gone over the time limit or if you've exceeded the memory allotment or too much storage or any number of other tasks. And so these are kind of the breakdowns that you have for these. And this is sort of important for understanding the big data concepts later and sort of appreciating how these structures look and how you can go about actually working with these systems. So we'll cover briefly this idea of databases, where basically databases you can think of as kind of like Excel tables or spreadsheets, where you just have rows and columns, and you have one database can have a number of different spreadsheets inside it. And so here we have an example where we have animals and cells. And so one table is animal, and you have sort of the animal ID and the weight. That's the two columns inside. And the other one is cells, where you have an animal ID, anisotropy, type, volume. And so this would be an example of a database you might be looking at. And the reason we're introducing this is so that you have some familiarity with SQL. Because before you can go sort of all the way to big data, you have to cover small data a little bit. And SQL is sort of the world of small data, or how data is processed today. And so, if you have these two tables, you can use this very simple command here, select volume from cells, to get all the volumes out from that table. And so it's just, select from, it gets it out. And if you wanted to calculate the average volume of all cancer cells, you could say select average volume from cells where type equals cancer. And so, of course, you could have done this task easily without using SQL, if you used Excel or R or MATLAB. But the advantage of SQL is that when you type in this command, it's declarative. And so it doesn't say, go through cells one row at a time, take all the values of volume, add them up together, and then divide it by the number of values that we saw. It just says run this average function on that column where type equals cancer. And sort of the main difference here is you've given the system unlimited freedom with how it does this task. So it's able to take this and divide it up over 1,000 computers and have each computer run a couple hundred rows in order to deliver that response. So you've completely separated what actually needs to be done, what data needs to be read in and read out and exported from the task itself. And so even today, sites like Facebook do a majority of their analysis in tools like SQL because you can analyze millions and millions of rows very quickly. And you can have a language that's sort of completely independent of whatever your backend is. And so here, this could be SQL Server, this could be SQLite, this could be a giant Hive database with 10,000 nodes on it. And that command looks exactly the same, but ends up being executed in very, very different ways based on what you're looking at. And so that's really, we don't want to go in more detail than that, but it just offers you sort of an appreciation for how these setups look and what sort of real declarative programming looks like. And so having an appreciation for this, I think, is quite important. And becoming familiar with this is very useful because it's being used everywhere for analyses today. And so the small data world consists entirely of this because it's very efficient and it's very good at handling large data sets well. I think we'll leave out those. If you're interested, you can look at them yourself. So if we go to sort of the big data, and so it took us an hour and 42 minutes to get to the core of the presentation, but the main part of this presentation, which won't be too long, don't worry, is sort of about big data after we've done all of that introduction that's hopefully given some background to why this is important. And so the first thing is sort of about the velocity, volume, and variety. And so this is when you have a lot of different type of data that's coming in quickly, where big data really becomes the only way to handle it in a reasonable manner. And so when you look at things like 8 gigabytes of synchrotron data a second coming from this camera, that's velocity, volume, and variety, because it's not like you're trying to do the same analysis with every image. You know, sometimes you're looking at metal foams and you're trying to count bubbles, and sometimes you're looking at pieces of bread and you're trying to see how much gluten is inside, and sometimes you're looking at a volcano and you're trying to look at how the magma flows. And so you have a lot of different tasks, which means you can't just have one fixed architecture that runs all the analysis. That if you look at like a GoPro used as a security camera somewhere, you know, it might be detecting faces, but it's not detecting faces, and maybe sometimes there's dinosaurs and it needs to detect them, or sometimes there's something else. It's just detecting faces and comparing them. And so it's not really a big data problem because it's doing the same thing. And so it just requires a certain few chips that are optimized to solve that problem, and then it can run very efficiently. And it only becomes big data when you're trying to then do a lot of different things. You know, if you had a camera set up where you were detecting faces and then you were trying to look at someone's behavior, you know, like at a train station, to see if they were going to jump in front of a train, or if they were being suspicious, maybe they were going to plant a bomb. That might be more big data because there's not a fixed, clear task you're trying to do. There's a lot of different tasks, and it might require tweaking and adapting things very frequently. The next point is sort of when scaling isn't scary. And so where 10, 100, 1,000 is the same amount of effort for what you're trying to do. It doesn't require any more manual effort on your part. Of course, it requires more computational power, but that's just a click away. And when you're starving for enough data. And so when you look at AmpLab at UC Berkeley, when you look at companies like Google, like Facebook, they sort of never have enough data to do the analysis that they want. So they always have a large amounts of data. I mean, they have terabytes, or if it's Google, petabytes of data they can analyze. But their limiting factor isn't their computational power, isn't their ability to write code, it's having enough interesting data to do their analysis. And then the last part is sort of 0 clicks per sample. And so that none of the work you're doing is manual at all. It's all completely automated. And so to kind of say where this came from is Google is probably one of the first companies to really have to deal with this. Potentially NSA before, but we don't really hear very much from what they've actually done with all this data. And so basically what Google ran into was this problem of making a good search engine. And so what they wanted to do is they wanted to rank all the sites on the internet. And so basically if you look at this even worse pseudocode, for every site on the internet, the current rank is equal to this secret PageRank function. And so they can just run this loop over all the websites of the internet and come up with a ranking. And so this was kind of their original thing, and this was their secret sauce. They had a really cool function here. And the problem was you have millions and millions, at that time, sites you needed to go through. And so if you wanted to run this efficiently, you had to break it up into a bunch of different pieces and have each computer handle a couple thousand, tens of thousands of websites to run your nice little secret PageRank function on. Unfortunately, Google got better, and they came up with a new PageRank function. And so what this one did is it didn't just look at the website itself, it looked at all the other websites that link to your website. And so if a lot of other websites with high ranks link to your website, then your rank goes up. And if a lot of pages with low ranks link to your site, then your rank goes down. And so this requires not just for every site on the internet, but it has 2 loops or a nested loop inside it. So for each site, you need to look at each other site to see if there's a link pointing to it, and then add or adjust the page rank if you want to do this. And so this becomes, of course, much more difficult. And so can anyone think of how you divide this task up?
How would we divide it up?
Yeah. So if you have 100 computers, how would you spread this out over 100 computers?
Is that back to the coin thing that we that we discussed at the beginning? Is it the same?
Slightly different, but it's now sort of more code. Or how would you split up the tasks to have it done quicker?
I don't know. I would do it in blocks. Like, well, I'm not an expert. I don't know.
No, you don't need to be an expert. It's much more of like the problem. And so blocks is a good idea where you'd say like
you get the best out of an X amount and get the best out or like one of the tasks that you want out of one block and then the other block and then the other block.
Yeah.
And then the sub things that will come out.
Yeah.
So know what I mean? Like a hierarchical.
Yeah. You could do that. The problem is that your biggest issue is that you have every site on the internet here.
All right.
And that means each block sort of has to have every site on the internet on it, or you have to find a way to divide that up.
Okay.
And so the problem comes that like if you were to make blocks, you may be able to make blocks like English sites and Chinese websites. And that you'd have all the English sites run on one computer and all the Chinese sites run on another computer. And then maybe you could break it down even further and like all the North American sites and then all the South American sites, or divide it by continent. The problem is that if you have sites that link across this, you can't run that analysis anymore, or you're getting the wrong answer because you don't have the list of all the websites on the internet. You now just have the list of all the sites in the same continent as you. And if you're a site in China and you have a lot of very valuable sites in the US linking to you, you probably want to include that in your page rank because that would make it go up. And so how do you handle that in a reasonable way? And it becomes a very difficult problem that you kind of can't divide it very easily because the sites sort of have links going everywhere. It's this sort of massive web that you can't easily entangle. And, if you get a really big, really fast computer, on the most powerful computer of the world, because Google tested this, one loop of their PageRank function would take months, which would mean they would require months to update their search index. And so, of course, that's not a feasible response either because, if you're a company like Google, you want to be able to update multiple times a day. if there's new information, you want people to be able to find it quickly, and you don't want to find information that's 90 days old if there's something much newer available. And so you kind of end up with this problem that it's a very tricky thing to kind of untangle this web. And even having the top computer scientists in the world working for you doesn't help you solve this problem more easily. And so what they came up are, it gets even better. You have a backup. What happens if a computer or a hard drive crashes? What happens if power goes out in one of your data centers? How do you make sure that your index still gets updated, your tools still work? PageRank doesn't just count. It uses the old rankings from that page, and then it sort of iterates until the ranks converge, which means you could run for tens or hundreds of iterations. And so if each iteration takes months, then it's obviously even less feasible to do all of this. And so what Google came up with was we need a new, better way to think about these kind of problems. And so what they came up with is this idea of Mapreduce. Has anyone heard of Mapreduce or Hadoop before? No one? Okay, this is all new. Good. And so several engineers at Google recognized common elements in the many tasks that were being performed. And they decided, or they realized, you could break everything up into two classes. One was map, and the other was reduce. And so for a very, very simple example, map is where you take a function and you apply that exact same function to every element in the list. And the function only depends on exactly that element. And so it's very sort of much in line with the mathematical definition of this map idea, where you have sort of a list here of 1, 2, 3, 4, 5, and your map function could be x squared. And so then your map of f to L would be 1, 4, 9, 16, 25. And so obviously that's not very interesting. Squaring a function was never a particularly difficult problem before. And so now that we have a new way of talking about it, doesn't really solve much for us. But the reduce idea is a little bit trickier. And so this then kind of goes beyond just applying the same thing to each block and focuses on how can you combine different blocks together, but so that they only have to know about the blocks that they see and they don't have to know everything else that's going on in the system. And so this is then sort of similar to the idea you had with the hierarchical blocks sort of coming together of, you find a partner, you add your numbers together, and then your partner sits down, and then you find someone else, add the numbers together, and that if you have a function like g of a of b, that the reduce then looks like g of g of g of g of, and so you can run that without knowing what's in the entire list. You just need to know sort of two pieces of it. You process it, and then someone else gets the next piece. And so it basically breaks the task up into a lot of little pieces to run. And so in this case, you can say for like adding, because it's associative, you can very quickly run add on all these different elements and break it up into tiny little pieces. And so Google's brilliance here, or I think his name Dean's brilliance with this, was that if you take everything you're trying to do and make it as map reduce operations, you can build one infrastructure that does maps and reduce really well on really large data sets, and then run any task you want using this infrastructure to get a good result out. And so that's sort of what makes this very interesting, is that you're no longer thinking about sort of where's the data being saved, how am I loading it in, which computer is doing which task. You have people who are focused on making MapReduce work really well, and you have people who can focus on breaking up complicated tasks into MapReduce steps. And so one of like the hello world, for the MapReduce test, what this looks like effectively is that you partition your data into different chunks across all the machines in the cluster. You apply a map to each element. You shuffle, repartition, or group the data, and then you apply a reduce to each group, and then you collect all the results. And so that basically this becomes your job that you're trying to run, or your task. And so with L, F, and G, you've sort of defined everything that you want to do in this analysis. And so now for a little bit more of a concrete example, we have here sort of counting words. And this is kind of the hello world of Mapreduce, where you want to count how many words show up, how many times in a bunch of lists of strings. And so here, your map function would be able to take a sentence and break it up into a bunch of words. And so, it looks something like this, where you're, for each word that's in your sentence, when you split it up by spaces, make one of these outputs. You then group by the word itself, and then reduce sort of adds all the keys together so you know how much each time each word appeared. And so here you have cat, dog, car, dog. Obviously not a task that you really need a big data tool to do, but that you can run map on it, then you get cat, dog, everything else. You can then run the shuffle to sort of group it by cat, dog, and car. And then you run the reduce to see that cat shows up once, dog shows up 3 times, and car shows up 2 times. And so that you can take something like word counting and break it up into this task that you can actually run easily on 1 machine or 100 machines, as long as someone has implemented this map, shuffle, and reduce well. You just give it those commands and it will run that for you. And so now we'll do this with all the lines of Shakespeare. And so all of this code is interactive, so you should be able to use it in your browser, so that if you run it, hopefully it works. So we can read in. We have all the lines of Shakespeare. I guess we can print how many lines there are. So there's 129,000 lines, and we kind of want to see which words appear frequently in Shakespeare. And so we can do the imperial or serial execution approach, where we basically say, for each line in Shakespeare, we take the line, we convert it all to lowercase, we strip away all the spaces that are unnecessary, we split it by spaces, and then we keep all the words, and then add +1 to each word for what we're trying to do. And so we can run this. I think we see it runs in a few seconds over all the lines of Shakespeare. And this is sort of the serial approach, the imperative programming style. And so this runs on exactly 1 machine. And if you were to deal with lists that were thousands of times larger, it would take thousands of times longer to do that step. There wouldn't be an easy way to make this code run much quicker. And we can print out the analysis here, where we see sort of he used 26,000 different words. The most frequent words were the, and, I, that, whatever. The least frequent were new bent, prevailment, unhardened, and filched, which I didn't know was a word, but apparently it is. So that you can run this analysis and sort of see what's going on. And now, how do we do this using Mapreduce? And so with Mapreduce, we can we focus on a completely different idea. And so here what we do is we want to make a function that goes from lines to words. And this is our map function. And we want this to sort of work really well. And so here we spend time saying, okay, we break up the line, we split it into different chunks, and then we return all the words that come out. And here we use something called unit testing or doc testing, where we actually have an example line and what should come out, that it automatically runs when we do this. And so if you change, so here it says it's okay, but if you say Bobby, it will then give us a failure that this test didn't pass. And so this is quite a nice approach when you're dealing with bigger data things, and I won't get into this in any detail, but where it's very important to make sure that these functions do exactly what you think they do, because once you start running it on hundreds of machines, it's a lot harder to figure out if they're making mistakes. And so having tests inside of them can make your life much easier. So here we use something called Dask, where we basically sort of make a bag from the sequence. And so this is sort of a tool like Mapreduce, but it works entirely in Python. And we can now apply this map operation. And so We now have this bag that has map applied to it. We can now sort of cheat a little bit on the reduce step, and so we use this function called frequencies, which basically handles that group reduce thing for us and makes it a little bit simpler. And then we can actually run it. And so we can go here, and hopefully it works. And so it takes a little bit longer than it took before, but it's now being executed on a number of different workers completely independently of one another, which means if we were to scale this to 10 times as much work and run this on an actual cluster of machines, it would be much quicker, and it still gives us exactly the same results. And what we can see here is we can now see what the profiling for this was. And so we actually had 4 different cores being used for each one of these tasks to get the results that we were looking for. And so that's sort of the major advantage of this, is that you've now assembled something that runs really well on a large number of different machines that is in this sort of Mapreduce paradigm. So Hadoop is sort of a Java-based tool to do this, and this is one of the first ones that comes out. We won't talk about that at all because it's not really used in the scientific community very much. Spark is sort of the subsequent tool to Hadoop. This is Java and Scala based and has some Python implementations, but it's still fairly tricky to use, and it hasn't really established itself in the scientific community. So there are certain areas like genomics or sort of business intelligence where Spark is used all the time. But for scientific analysis, there's very few groups who are actually doing this. And Dask is sort of what we used in this notebook and what sort of examples we'll stick with for now, because it's a very core part of the PyData setup for Python. And it's much easier to use because you don't require any Java or any other tools in order to run the code that you're trying to do. And so we have this idea of sort of directed acyclical graphs, which is where you have a process that's defined as sort of a graph rather than being defined as a sort of imperative list of instructions. And so this idea is sort of the actual realization of what we were calling declarative programming before. And so last time when we were talking about sort of the imperative and declarative versions of these soups, what we really meant was having a DAG that looked like this, where it's sort of buy vegetables, then buy meat, then chop vegetables, then heat water, then do all of these steps, to going to a DAG that looks like this, where you sort of have different tasks you can execute, and for each thing you're trying to do, you can see what the dependencies are. And so here you see that if you want to make a soup, you have to buy meat, and then you have to add vegetables, and then you have to execute these things, but you allow a more complicated infrastructure to come in and say, we can run all of these on different cores, or we can run this on this machine because it's much better at getting vegetables, and this one's much better at heating water, or whatever that might be. But you give it the level of detail it needs to execute it efficiently. And so whenever you can make DAGs like this, you can make your task much more efficient. And so here's an example from Facebook's AI research group, where you have this fairly simple command. And so what this command is sort of a local average. And so it takes an image as an input, and it averages all of the values in a certain region in order to sort of tell you what the average in that region is. And so it's called average pooling. It's used very frequently in deep learning. And what we see is that, if you generate sort of standard code from this, which is sort of an imperative function, it's very inefficient. And so it can take, I think, 13 milliseconds to execute one iteration, which might not seem very long, but if you're running an operation like this millions of times per second, that becomes a very long time. And this is sort of code that they used in their face detection algorithm. And so with this, if you have this kind of DAG representation, you can now generate really efficient implementations. And here you see you can get down to 42 microseconds for running this actual function, because you have tools that are able to do the so-called tensor comprehension and take the code that you're trying to run and come up with a much, much more efficient implementation of that code. And so this is particularly important when you're dealing with like GPUs, because GPUs are really optimized for certain kinds of tasks. And so if you can fit the analysis you're doing with the tasks that it's optimized for, you can get huge performance improvements. And so we can do the same thing with Dask quite easily. So you have this tool in Dask called sort of dot graph, where you can make it show you the DAG for the operations that you're making. And so Dask is lazy, so when you do anything here, it's just making graphs. It's not actually executing any code. But we can go here and we can sort of say image 1 is zeros broken up into little chunks. We can then add two images together, multiply 1 by 50, and we get this whole graph out of operations that need to take place in order to compute that final value. We can do things like matrix multiplication, where we then get more complicated graphs. And we can move this to sort of a real-world image processing problem. And so here we have an example of a foam, which is 100 by 200 by 200, but you could obviously do this on much larger images, and that's what's included in the link below this. And you can show the foam here. Do we see it? Yeah. So you can use this to sort of preview what that structure looks like in Jupyter quite easily. And now we can break it up into little chunks so that we have our image broken apart into little pieces and start to actually process with it. And so here we can make sort of a Gaussian filter on our image and see sort of the whole graph that gets generated of operations. And then go, a binary erosion to sort of get rid of some of the things that are connected and make it separate into separate entities. And then a labeling task. And then run sort of our analysis. And this will be then run on a number of different cores in a very efficient way that's automatically handled for us. And we can sort of see which tasks were processed on which core at which time. And, for example, if we just want to grab slice 50 and we don't want to grab the whole image, we can visualize sort of the optimized graph where we see sort of what was the littlest pieces of information we needed in order to actually extract slice 50. And so here we see, you don't need all of the foam images, you just need these 3 blocks of it in order to calculate what that slice is and run the Gaussian filter and get your answer. And so by doing things in a lazy manner with these DAGs that you have the computer optimized for you, you can end up doing very complicated analyses and automatically sort of pruning the parts that are important. And so I think that's where I'll stop. We have, if you go back to the original site, an example here on sort of a larger data set, sort of applying big data approaches to tomography data. And this is then on Kaggle, where you can see how you apply it to, what's the data size here? 200 by 2000 by 2000. And so this one you require a little bit more memory to do, but you basically go through and run a full image processing analysis using Dask, which means if you ran this on one computer, it would run at least on all the cores, but you could also run this on a cluster and have it run much, much quicker. And so it allows you to do these analyses very easily in a number of different ways and sort of explore with the ideas of big data in doing these sort of approaches. So are there any questions, I guess, on that? Nothing.
The coin issue is still bothering.
The coin?
The median of the different coins that we have.
You have to sort it and then choose.
No,
They can sort them on themselves.
Can they?
Yes, I mean you say you ask who has it bigger, then you stay in a row, and then the middle one would have the middle
I think you sort it,
Amount
then
of
you
points.
get a median out of a block, and another block, and another block, and then you get the median of that, and then you get the median of that, and then you have a median at the end.
But is the median of
All
medians?
the blocks are the same size.
I mean, you could just once sort it with this bubble thing.
But inside each block.
Altogether.
Well, if you put it all together, then you have to copy all of them onto one machine, which is fairly fast, but it's not the optimum solution. And particularly as you start to get to thousands and tens of thousands of computers, it's a lot of data to send back and forth.
Can you first do the map, like run everything and make a graph, and then separate blocks by using, like, we're not talking about size, right? And evaluation.
Oh no, I think we're talking about the median problem. Or I thought you were talking about the median.
Yeah, the median problem. Yeah, I am talking about the median problem. I don't know. Because we haven't found a solution.
Well, one person had an idea.
Who? Give us a hint. I don't know.
What happens if you have like each of the computers with each separate lists and their median and how many numbers you have below and above that median?
Yeah.
For example.
Yeah. So that's close. That would be the hint I would have given. But so basically what you can do, since I guess you've had enough time to think about it, and there's lots of other similar problems that require lots of creative thinking as well, is that you can basically say, you can get the mean very quickly, and this gives you a starting point. And then you can just ask all the computers, how many numbers do you have above this value and below? And then you can just iterate. And so if you have too many that are above, you increase your number, and if you have too many below, you're decreasing. And that you can iterate and get very close to what the actual median value is by collecting this information. And if you have some computers that have
So
10...
you assume the median first.
You guess. Yeah.
You guess it. And then you see that above. Okay.
Yeah.
That's easy.
Thought you could do the same with the people with the coins. You just ask one person at random, how much money do you have?
Yeah.
And then you say, does anyone have more? Whatever it was, not naming money, but
Who has the most money?
yeah. So where do you want to find?
Yeah, you could do that iteratively as well, where you say...
Yeah, anyone has more?
Yeah.
Yeah, okay. Then does anyone have more than this?
Yeah.
Etc.
Yeah. But in the worst case scenario, you end up talking to everyone, right?
In the worst case, yes.
But if you have a setup where you can get people or get nodes to work together with each other without involving sort of the master node, you can get things to happen very quickly. And so that's sort of where you want to have these sort of benefits of scale, is by getting as many of those tasks to be sort of handled independently. Because sort of your bottleneck with a lot of these things is communication with the master, that the master can only do so many things at the same time. And if you can break that up better, you can make it work well. And that's sort of where a lot of the difficulty comes in with Mapreduce stuff, is coming up with the right reduce step that can be executed independently. That, for addition, it's very easy, but if you're doing something like a Gaussian filter or counting components or looking for cells, that reduce function is not quite as obvious what it should be. So, okay.